In this video, we'll be looking at logarithmic functions and their graphs. These tie into the exponential functions we were talking about last week because logarithms and exponentials are inverse functions of one another. Our focus will be mostly on how to solve these equations and get exact numbers or decimal approximations using a calculator. Whereas when we are in a face-to-face class, we focus a little bit more on some of the calculations you would use without a calculator. When we were talking about exponential functions last week, we had examples such as y equals 2 to the x power. And we said that when we were going to consider an inverse function, we would take the x and the y variables and we would swap their location. So that's what's happening here in this new function that we're getting. And if we plot a bunch of points and look at them together, we can see that the graph of a logarithm is a mirror image across the line y equals x of an exponential. Again, inverse functions are reflected across the line y equals x, and that comes from the interchanging of the variables. A couple of key things we want to take note of. For an exponential function, we have an asymptote at the x-axis. For a logarithmic function, we have an asymptote at the y-axis. I can see for the exponential function that as the graph increases, as x gets larger, the graph is going up towards positive infinity, growing exponentially. But as x increases for the logarithm graph, the graph is increasing, but it's increasing very slowly. One of the common applications for a logarithm graph is a person's height over their lifetime. You do continue to grow throughout your lifetime, but it's at such a slow rate it doesn't seem like you're growing at all. It seems like your height has stayed the same since you were in high school. Looking at the graph, we can see that the domain of a logarithm function is going to be x values that are strictly greater than 0. And in fact, if we plugged into a calculator, let's say log base 2 of, let's say, -5, we're going to get an error message. Now, when we talk about graph transformations, where we maybe move the graph around, the domain's going to change. But in general, if there's no kind of shifting in the graph, the domain is going to be all numbers that are strictly greater than 0. We read a logarithm as log base a of x. So x is considered the argument, what we're taking the log of, and the base is the number a. It's a little bit slightly lower than in line with where the log is written. These are all logs that you can enter into a calculator. I'll show you how to enter these into Desmos in just a second. But notice that the base is given for some of them. In letter G down here, there's no base written. And that's because if there's no base written, that we consider to be the common log, and that is base 10. If there's no number written, then that means that the base is equal to 10. Calculators used to not have the option for different bases, and so you would only have two options. One was base 10 and the other was base E, which we'll talk about in just a little bit here. But now most modern calculators will allow you to type in a different number, like 2 or 8 or 6, as you can see in these examples. For letter G, we know that this is going to give us an error message, right, based on what we were just talking about, because -5 is not within the domain of a logarithm. All right, let me pause for a second and bring up Desmos. So I'm in Desmos now, which is the calculator that most of you are using for this class, and I'm going to show you how to find the logarithm options within this calculator. Over on the right, if you click on the functions option and then go all the way to the right with the miscellaneous, you'll see that you have log, that's log base 10. One of the examples that we just had was log base 10 of 1,000. Oops, why is that not working? Let me do that again. There we go. Didn't like the comma, which is 4. What that's saying is that 10 raised to some power is equal to the number that's in parentheses. 10 raised to the 4th power is equal to 10,000. The second one we had was, I'll use this button here, log base A. Log base 10 of 0.01, and it's telling us -2. That's saying that 10 raised to the -2 power is equal to 0.01, or log to the -2 power is 1 over 100. Remember that negative exponent means that the number belongs down in the denominator. Another example we had was log base 2 of 8. This is saying that 2 raised to the 3rd power is equal to 8. We had log base 9 of 3. And the answer it's giving us is 0.5. Remember that if you raise something to the square root, the power is actually 1/2. So 9 to the 1/2 power, or the square root of 9, is equal to 3. We had log base 6 of 1. This means 6 raised to the 0 power is equal to 1. And then the last one was log base 8 of 8. 8 to the 1st power is equal to 8. Now, oftentimes when you're using a different base, you're plugging in things like log base 5 of 7, and you're getting some random decimal number. This is saying that if you take 5 and raise it to approximately the 1.2 power, you'll get the number 7 back. So to reiterate some of the ideas that we just saw in Desmos, we have this first example property here that when you have any base, a is going to be any number, and you're taking the log of 1, that means that the answer is going to be ending up being 0. So another way to say this is that a raised to the 0 power is equal to 1. For that second one there, looking at this is saying that a raised to the 1st power is equal to a. Again, the base is the number that's sitting slightly lower. The exponent is across the equal sign. And the argument is the thing that we're going to put here and here, right? So what I'm doing is I'm using this idea of number of this I'm using this property here, which allows us to change between logs and exponentials and exponents. The base number is here, here's the base. The exponent is here, here's the exponent. And then this number goes on the other side of the equal sign. You want to memorize this. In this example, they want us to rewrite these as exponentials. This is saying 2 is the base, the exponent is across 2 to the 5th power is equal to 32. That's true. We're going to have things with variables in them that we're trying to find the missing value for the variable. So we'll have something more like letter B, where we're saying, okay, a is the base. A raised to the 8th power is equal to some letter Q. Letter C is written kind of in the opposite way, but the base is t, the exponent is across the equal sign, t to the x power is equal to m. We could put this in parentheses, and when something's in parentheses, and that's what we're taking the log of or the function of, that's called the argument. You probably saw in Desmos that we had 3 options for taking logs. We had log on its own, we had log with a little option for a different base, and then we also have ln. So again, this is log base 10. This is log of any base. Right? You can plug any value in that you want. And this one is log base e, meaning the exponential function. We had a couple applications from the last section talking about continuous growth with population models and things like that. So again, in a calculator, you could just plug these into Desmos and get the answers out. I'll pause for a second and then type those in for you. So I have gone ahead and typed in the examples that were in that last slide for you. Again, if you click on the functions option on the right and then select the fourth option here, miscellaneous, you can see natural log sitting down here. And I typed in the values and it's telling me that e raised to about 13.4 power would give me this number, 645,778. Here's another example. E raised to this negative exponent is going to give me this decimal answer. For the third option, it's saying e raised to the first power gives me back e. And for the fourth option, it's saying e raised to the 0 power gives me 1. So again, if you want to type the letter E, you can just type the letter. In this case, you don't have to find a special variable or anything. The examples or the ideas that we're going to skip over because we don't need this so much anymore. Before there were advanced calculators and things like Desmos, you had calculators that only had log base 10 or log base e. And so if you wanted to do a calculation for a different base, you would have to use this change of base formula. But as you saw in Desmos, you actually have the option to type in any number for the base. And so this change of base formula isn't terribly useful anymore. But just to kind of let you know how I memorize it, I think about the new base that I want. Often, again, A is usually either 10 or E. And the number that's slightly higher, the M, goes up on the top. And then the number that's slightly lower, the base, goes down on the bottom. So a log is just a ratio, and this is just saying you can take the relationship between this ratio here, split it up into the fraction, and change what the base is. Don't need to worry about that so much because you can just use a calculator. And I just wanted to show you 3 graph transformations of a log function. And it's going to follow the same ideas that we've been talking about for other functions. When we add a number inside the parentheses, it's going to move the whole graph to the left by 3 units. And so in a normal logarithm graph, the y-axis is an asymptote. We can see that in this particular graph, the line x equals -3 is going to be the asymptote. The asymptote shifts over to the left. Log graphs all pass through the point 1, 0. Let's see, what does that mean? I'm saying that all logs pass through the point one, 0. So if I have log base b of x is equal to y, that means that if I put log base b, I'm going to put 1 here for x, and then I'm going to put 0 here for y. It's saying that b, no matter what the base is, raised to the 0 power is equal to 1, and that's always true. I'm bringing this up because if a normal log graph would pass through that, but the whole graph has been shifted over to the left by 3 units, the new point that it's going to pass through is over here, -2, 0. So you can see that that point of intersection has been shifted over by 3 units to the left as well. For the second graph, we are adding 3. So this is going to have the effect of shifting up by 3 units. This negative is a reflection. And then the 1/2 is going to act as a vertical shrink. right? I can see the reflection. The graph normally would be here. It's been reflected, but then it's also been shifted up by 3 units. So let's take this point as reference, go up 1, 2, 3. I can see where it is up here, right? The whole thing got shifted up, reflected, shrunk a little bit because of the 1/2. We haven't moved this graph left or right, so the asymptote is staying at the y-axis. This graph here, the last one, the -1 is going to move the whole graph to the right by 1 unit. And I can see then instead of being at the point 1, 0, it's actually intersecting at the point 2, 0. Now, if I did not have absolute values, this graph would have come down like this, right? That was what the normal graph would have looked like. But this particular portion of the graph got reflected up here. Absolute value is going to take everything and make it positive. And that's how we're getting that particular graph. This is one of those special cases that we talked about in the past where we would call this a cusp, right? A cusp is where we have a curved portion of the graph and then another curved portion of the graph. So this particular point here would be called a cusp. And when we get into Math 150 in Calculus 1, we might have trouble taking the derivative at that particular point. All right, that's all for just the basics of logs. For the next video, we'll be looking at some properties of logs that we'll be using to solve equations. Thanks for watching.